greatest common divisor. Again, 1001. Again, just as a review. Remember what 1001 is? 7 times 11 times 13. You will see that many times in your life. Greatest common divisor. One way is to try to factorize 1008. But maybe there's another way. If you look closely at these two numbers, they are close. These are only 7 apart. So if you think, how can I have a common factor between these two? They are only 7 apart. I cannot have 11 in common between these two. This is divisible by 11 already. 1001. And the next multiple of 11 is, I would take 1001 plus 11, which is 1012. It jumps over. Again, you may already know an algorithm which can be used to do this. But I want to share with you how you would even think of that algorithm. And that's why I chose these two numbers so close by. I can't have an 11 there. It's too far. 13 is even worse. Next multiple of 13 is 1001 plus 13, which is 1014, even farther. So I already know from looking at this that 7 is the only possibility. 7 is the only possibility, and well, 7 has to be possible because this is by plus 7. So if this was a multiple of 7, then 1008 is also a multiple of 7. So this is not an algorithm. This is just some observations about 1001 and 1008 that make us think maybe there's a way to find GCD without factoring. And for that, now, let me share how we were thinking. What we were thinking here is actually that there's something unusual about 7. 7 is the gap between these two. Here is a fact that is true. The GCD between 1001 and 1008 is actually equal to the GCD between 1001 and 7. And the important thing about 7 here is 7 is just the difference between these two. Okay? But these are equal. And that's what we just did in our head. I want to now test this. I want to prove this, that this is true, completely true, without even using that 7 is a multiple, 7 is a factor of 1001. I don't even want to use that fact. I just want to prove these are equal. For that, I need to think about what GCD means. GCD means greatest common divisor. So in order to prove that these two are equal, it's enough for me to prove that every divisor of both 1001 and 1008, here's what I need to prove. Every divisor of 1001 and 1008 is also a divisor of 1001 and 7. That's one thing I need to prove. But I also need to prove the other way, backwards, which is that every divisor of 1001 and 7 is also a divisor of 1001 and 1008. this is how you will know that the biggest divisor of the left side is the same as the biggest divisor on the right side. Because every divisor of both on the left works on the right, and every divisor of both on the right works on the left. Okay? Well, how do I prove this? Let's do them one step at a time. I have the green one first. I need to look at every divisor of 1001 and 1008, showing it's also a divisor of 1001 and 7. Well, one part of it is very easy. This part. Because I said it's a divisor of 1001 and 1008. So, yes, it's a divisor of 1001. Definitely. Definitely. How about the other piece? The last part I need to check on the green is that every divisor of 1001 and 1008 both is a divisor of 7. What does this mean? You see, divisor of 1001 and 1008 means that, well, let's say every. So I need to call what it is. So I suppose x is. Suppose x is one of them. When I say one of them, I mean it's a divisor of both 1001 and 1008. Well, what this means is that 1001 is equal to x times some number. I'll call it a times x. A is an integer. 1008 is then something else, b times x. Different integer. If these are both true, what you'll see is that where did the 7 come from anyway? 7 was subtracting 1008 minus 1001. So if I subtract them, then I find that 7 equals b minus a times x. Perfect. b minus a, I subtracted two integers. So this is also an integer. And that means that x is a divisor of 7. Actually, why I did this so slowly is because this also shows us a nice calculation trick I can use. This shows us that if x divides 1001 and if x divides 1008, then that means that x divides their difference, 1008 minus 1001, which is their difference of 7. If I have two things that divide, I can subtract them, and it divides. Actually, while I see this, this also means I can add them. I could also take x divides, add them together, 2009. I'm showing you the kinds of calculations you can do with the divides. Okay, reason I talked about the add is because let's look at the other piece I need. The other piece I need is that if I have a divisor of both 1001 and 7, it needs to also be a divisor of both 1001 and 1008. Well, this is easy because I already know it's a divisor of 1001. How about the 1008? Now let's use that calculation method I just showed you. You see, if I have some divisor here of both of these, then what I have is I have some x, so let's call this x. Then I have that x divides 1001. Then I have that x divides 1001 and x divides 7. So, because we can add them together, like what I just did last time, x divides 1008. And throughout this entire calculation, throughout this entire proof, I never used the fact that 7 actually divided 1001. I don't need that fact. Let me really emphasize that. In this whole thing that we did, we didn't use that 7 divides 1001. This entire thing we did is just based on this observation that if I have x divides two things, x divides the difference and the sum. Because of this, we have a very special way of calculating GCDs. If these two are equal, here I was already done. But now let me just try any other numbers. Like GCD of 24 and 60. If I know now that the GCD of two numbers is equal to GCD of, keep one of the numbers and replace the other with the difference. I'll keep the smaller one, that will be convenient, and I'll replace with the difference, which is 36. The important thing here is that there's this gap, and that is my 36. My 36 is the gap. Okay, but if I already know this is true, I can do it again. GCD of 24 and 36 is equal to GCD, keep the 24, and what's the gap? The gap is 12. You may say you already know what the GCD is, but I'm doing this all the way on purpose because we're going to do something with it next time. Now, GCD of 24 and 12 is equal to, it's easier for me to flip them around because I'm always keeping the smaller one in front. Of course, it won't matter if I flip them around or not. 24, that's the same two numbers. GCD of 12 and 24 equals GCD of, you keep the first one and you replace the second one by the gap. 12. Now this one, whether you know anything about number theory or not, the greatest common factor of two identical numbers is themselves. This is one way of seeing GCD is 12. I did this very slowly, but this can be done now fast, and I want to use this same method to try on the original numbers from last time. If I want the GCD of 1001 and 728, now we can do this very fast. I'm not even going to move them back and forth. I always know I keep the smaller one alone. So this is going to be GCD. Let's keep 728 here. Now I actually need to subtract those two. And if I subtract those two, it looks like I have 11 minus 8 is 3, 9 minus 2 is 7, 9 minus 7 is 2. Okay. Well, if I continue with this, I could do several subtractions, which I guess I can do that right now. So this is equal to GCD. I need to subtract a few times. So if I subtract 728 minus 273, 8 minus 3 is 5, 12 minus 7 is 5, 6 minus 2 is 4, 455. So I have 273, 455 equals GCD of 273, and again I need to do a calculation. 455 minus 273, 5 minus 3 is 2, 15 minus 7 is 8, 182, and that is equal to GCD. I'll keep my 182, and now I'll take 273 minus the 182, 3 minus 2 is 1, 17 minus 9 is 8. 17 minus 8 is 9. 91, we're almost done, because the last one will be GCD of 91, and if I subtract those, I get 91, which is the 91. And so these are two different ways of doing the same thing. This way here, I did not do any division. I just did subtraction. So this shows that when you find GCD of numbers, you don't actually even need to prime factorize. Why is that important? When you're doing problems, for some problems, prime factorization is easier. For other problems, you don't see the primes ahead of time. And subtraction is very easy because there's no guessing. If you subtract, you just subtract, and you hope you don't make a mistake. This is one use of the Euclidean algorithm. I just mentioned what this is called, so I should write that down. This whole thing here that we did today is called the Euclidean algorithm. Euclidean algorithm. This is the use of the Euclidean algorithm that most people are familiar with. It's to find GCDs, and all you do is subtract. There are more uses of it. We'll discuss that next time.